Hello, Christian Grabenhaft from the University of Liverpool. In this video I'm going to be looking at the bearing capacity of these types of structures here. Bucket foundations, suction bucket foundations, suction caissons, call them what you want. They work as shown here, so it's basically a skirted foundation, you could say. It's an inverted bucket that you lower onto the seabed, and then probably depending a little bit on the properties of the seabed, it may penetrate more or less into the seabed. And once that penetration is done, well, then you start basically sucking water out of the caisson. So in that way create a lower pressure on the inside than on the outside, and in that way you well, pull or push, depending on how you look at it, the caisson into the seabed to eventually end up with a situation like this over here. And so this is a fairly popular solution for offshore structures, oil and gas, wind turbines, this kind of thing, and you can use them in sand or in clay, and you can use monobucket type structures as shown here. You can combine them in a say a tripod type structure, like this. So we are going to be solving a problem of just a single mono bucket, and I've been looking at a paper here, Holsby, Ibsen and Byrne, suction caisson for wind turbines, from the 2005 ISFOC conference, and I was particularly interested in this figure here that shows the typical loads on a 3.5 megawatt offshore wind turbine, and we're going to apply the same loads or these loads here in the G3 analysis. So let's switch to G3, and I thought before we get started with the full problem, it might be useful just to solve a much simpler problem that can then also be checked in G2, just to see that we are doing things properly, that we're getting reasonable results and so on. And so I've defined a soil domain here, and what I'm going to do is simply a centrally loaded bucket foundation, and I'm going to consider 1/4 of the model. So a fairly standard problem that can be solved, of course. That's the idea in G2 as an axisymmetric problem. So radius, let's say 5, and a height of 10 meters. So a diameter of 10 meters and a depth here of 10 meters as well. And so I will delete that, and that's pretty much the geometry. Then we need to, of course, model the caisson itself, and I'm going to do that using shell elements. But let's apply some soil, and I said we were going to use sand, so let's have a loose sand and see a standard more Coulomb material, 0 cohesion, and a friction angle of 30 degrees. The unit weight, well, if we are underwater, we should really be using the effective unit weight, so let's say that's something like 10. And then to apply the shell elements, well, I first need access to this part of the domain where they should be applied. So I hide that part, and I now have access to the back here of this quarter cylinder, where I can then apply shell elements, and to the both here and here. I don't know what happened there. So shells, and hopefully you can see that interfaces are included automatically as well. Now the shell is an unfortunate color. It's kind of similar to the soil, so let me make it, say, green. So then you can hopefully see the shell turn green here. that. Good. Let me unhide that, and then loads. So I'm going to do a limit analysis, so a multiplier load, and I'm going to set that to 1,000 so that we get the results in basically in megapascals, right? So apply 1,000 kilonewton per square meters, and then find the multiplier that will bring this load to collapse. And then standard fixed T's, and also very importantly the shell BCs. And the shell BCs, well, we can constrain the displacements in 3 different directions, and then the rotation normal to the line here, so, or corresponding, not normal to the line, but corresponding to bending about this line here that we have selected. And we're using a local coordinate system here. That's the system shown up here, and the X, Y, and Z, the local X, Y, and Z are not shown. You have to use the color codes, and the color codes follow the global system, so X, Y, Z, red, green, blue. So here we basically need to support the shell in the Y direction, in the green direction, and keep it free in the other 2 directions, and of course no rotation about this, about the x-axis. It is in this case. And for the other one, same thing. Again, Y is the direction, local Y is the direction normal to the plane of symmetry, so we keep that fixed and then free the 2 others. And then we are pretty much in business. There was just one thing I forgot, and that was the properties of the shell. And this should be a rigid shell, so, and let's make it a rigid weightless shell. You can use a rigid plastic shell, so a shell with actually a finite strength, but it's just for the sake of simplicity, assume that the shell is strong enough. Okay, and I think we are all set up. We're going to do a limit analysis. We're going to use the mixed element as usual. Let's just start with 1,000 of those, and let's have some adaptivity as well. And then let's go and see what we get. And while we wait for that, I am going to start up G2 and set up the problem in G2 as an axisymmetric problem. So turn on the symmetry axis and then draw this domain. I think it was 50 by 40, like that. And then the foundation 5 by 10. That's here. Delete that one. Apply a loose sand MC, and the unit weight should be 10. The effective unit weight in G2, we could of course have used the water table tool as well and then operated directly with the saturated unit weight, but let's just keep things dry and then use an effective unit weight. The shell modeled as rigid plates, and like that. And let's do a lower bound analysis, and let's then clone this stage and do an upper bound as well. Okay, so I think this is all good to go, and let's go then. So and well, we can see what we have in G3. We have 8.257 and a collapse mechanism and a plastic dissipation or shear dissipation field that looks like this. Maybe we should have made actually the domain slightly larger, but we will have to do with what we have here. So that looks, I think, as expected. And let's see what we have with G2. Well, we forgot to multiply by 1,000, so we'll have to divide by 1,000 here in order to compare directly with G2, so G3. So we have 7.5 for the lower bound, and for the upper bound 8.5. So the mean value here is 8, and in G3 we have 8.2, 8.3. Quite often the upper bound is slightly better than the lower bound, so I'll consider this verification a success. We get the same result in G2 and G3, and that result is very close to the true solution. And that again, I've talked about that in other videos as well. This mixed element is really very accurate, especially when combined with adaptivity. You can usually do with a few thousand or a few thousand elements and get something that is very close to the true solution. So let's get started on the actual problem. This problem here. Okay, and I am going to try to use a foundation that has a diameter of 10 meters and a depth of 10 meters as well. And I'm going to model the full problem. So let me draw a domain like that, and 40 high should be enough. And then a cylinder at 0.40, radius of 5, height of -10, and apply some material for the solids, soil, again the loose sand MC, and that has been reset because I started a new problem, so unit weight of 10, corresponding to the effective unit weight, so the saturated unit weight minus the unit weight of water. And features, again, we want shells, so let's hide that, and then let's apply shells here like that. And we could try to change the color again. There was something wrong before, I think, but let's see if it works now. Yes, that works now. So we have a green shell, and we have interfaces as well. I forgot that in the previous run, that we actually have interfaces automatically applied to these shell elements. By default, the material applied at the interface is the same as the parent material, as the soil material, and we can then apply reduction factors, so reduction in the strength, or in this case the friction angle between the shell and the solid, the soil. So if we are talking steel, sand, well then Eurocode 7, as far as I remember, says the reduction factor is 2/3, so we can try to use that. Like that, and same at the top here, 2/3. Good. On height and standard fixities, there's no conditions for the shell. In this case, it's simply just applying the load. Well, yeah, not just applying that load, of course. We want to apply these loads here. And so that's a vertical force of 6 meganewtons, a horizontal force of 4 meganewtons, and a moment of 4 times 30, 120 meganewton meters. And there's a previous video where I showed how to apply a given set of loads and moments to a foundation, to a sort of a surface like this. But I think for the sake of simplicity, in this case, we might just model the actual pylon. So let's actually do that. So let's create a box. That's the simplest way of doing it, of course. Create a box with a cross-sectional area of 1 meter. Oh, that went completely wrong. I was trying to punch in the coordinates there. and 0.5, 0.5. That's the base, and then a height of 30 meters. And let's make that rigid, and like that. And we can then zoom into the top here and actually apply the loads up here. So that was six, let's just see, 6 meganewtons vertically, 6,000, and horizontally 4,000, like that. So we have an inclined load up here, and so we're ready to go. Again, some adaptivity, and let's see what we get. Well, that seems a bit low. I think something's gone wrong here. Something has definitely gone wrong. Yeah. And what has gone wrong is, of course, that I forgot to change the shell to be rigid. So it breaks immediately like that. I mean, the pylon just breaks off like that. So that wasn't very fortunate. But that's what happens sometimes. Let's just wait for that to terminate. It happened there, and I think in the future I'll actually make rigid weightless the default option. Let's go. That looks more along the lines of what I'd expect. So a collapse multiplier slightly above 1, meaning that we can sustain these loads, but not much more. And well, it looks like this. So there's a sort of a good separation between the caisson here at the back on the active side and the soil. I think we should provide some sort of entertainment for these waiting times. What do you think?
What was that?
I think we should provide some sort of entertainment while people are waiting for the results
Yeah,
to come out.
that's a good idea.
I don't know what exactly.
Inspirational speeches.
Inspirational speeches, yeah, maybe something like that. Okay, so we're done. 1.23, it didn't really change much from the first adaptivity step, and that's quite typical of this mixed element. And well, it looks like this. I can't say it's totally unexpected, and yeah, well, see the meshes, of course, been refined around the caisson, and this is how it looks. So till next time.